Hello there, ladies and gentlemen. Today we'll be looking at how do we find rational roots of a polynomial. In the previous video, we looked at how to find integer roots. We're going to expand that now to all rational roots. So if we have a polynomial f of x, looks like so, with leading coefficient not equal to 0, and there's a rational number, p over q, where they're relatively prime, p and q, that is, the greatest common divisor of them is 1, such that when we plug p over q into function f, we get 0, then the numerator p will be a factor of the constant term, and the denominator q will be a factor of the leading coefficient. Okay, cool. Now, just like with the integer zero theorem, there's a corollary that goes along with this. And it says that if we have that polynomial where we have integer coefficients, leading coefficient not equal to 0, and a rational number p over q where p and q are relatively prime, such that it is a 0 of the function, then for any real value k, p minus q times k is a factor of f of k. These two theorems, or the theorem and this corollary, are both provable. It's not something we're going to do today, though. We are simply going to use them to answer this question. Given that we have this polynomial, f of x, it has 0 integer zeros. We want to find its only rational zero. So this problem is giving us a hint. It's saying that there's only one number that's going to be a rational number. And since there are no integer zeros, the other two, because if you notice we have x cubed, the other two roots are going to be either complex or irrational. So let's go ahead and use our rational root theorem. Our p comes from the constant term, and it's going to be plus or minus 15, plus or minus 5, plus or minus 3, plus or minus 1. Those are all the factors of 15. Our q comes from the leading coefficient, so that could be plus or minus 2 or plus or minus 1. So p over q will be this set of numbers. I'm just taking and making a ratio out of every p and q possible combination that there is. So I'm taking every p over every q. And this is a fairly long list. What I could do is I could use synthetic division and check these one at a time until I come across the right one. That corollary, however, can come in quite useful to narrow down this list along with Descartes' rule of signs. So I'm going to start out and find f of 1. 1's a nice number to plug in. It's easy to substitute and get a value. So we get f of 1 equals 2 minus 11 minus 11 plus 15, which is equal to negative 5. And that tells, the corollary tells me that p minus 1 times q has to equal factors of that. So p minus q, in other words, the numerator minus the denominator up here in blue, has to either be positive or negative 1, positive or negative 5. So let's go through. 15 minus 1, that doesn't work. 15 minus 2, that doesn't work. 5 minus 1 is 4. That's not going to happen. 5 halves, 5 minus 2, no. 3 minus 1, no, that won't work. 3 minus 2, that's going to be, 1. What about negative 3 halves? Negative 3 over 2 Negative 3 minus 2 is negative 5. So both of those are solutions. So I've now sort of narrowed this down. P over Q could be 3 halves or negative 3 halves. Are there any others? What about plus or minus 1 over 1? If I subtract there, 1 minus 1 is 0. Negative 1 minus 1 is negative 2. 1 half. 1 minus 2 is negative 1. Negative 1 minus 2 is negative 3. So the negative part does not work, but the positive part does here. So using this corollary, now I only have 3 possibilities for a rational root. And at this point, again, I could use synthetic division, or we can look at Descartes' rule of signs. So for f of x, the signs go positive, negative, negative, positive. There's 2 sign changes, which means there are 2 or 0 positive roots. And I've got 2 positive roots here, but it tells me there's only 1 rational 0, so that doesn't help. So let's look at f of negative x for Descartes' rule of signs. There we end up with negative coefficient, positive, positive. So this says that there's 1 negative root or 0. But if there are 0 positive roots, that means there has to be 1 negative. So there is our only rational 0. And let's look at what we can do with this now, because we can actually do something kind of nice and cool, and we can actually factor this polynomial. Let's use synthetic division. 1, to verify that this is indeed a 0, but 2, I'm going to use it to help me factor this polynomial. There are the coefficients. We drop the 2 down. Now we multiply and then add. Multiply, add, multiply, and we get 0 as a remainder. That's good. So what does this tell me? Well, it tells me that when negative 3 halves is a 0, x plus 3 halves is a factor, and my other factor, which becomes quadratic now, is right here. 2x squared minus 14x plus 10. This is f of x. And now if we do a little bit of playing here, notice the quadratic of 2 can be factored out. And I'm actually going to send that 2 into the first factor that I have here. So 2x minus 3 times x squared minus 7x plus 5. And correct with what we were told at the beginning, this second factor, that quadratic, is not factorable, which means there are no more rational roots. So what we've just done here is pretty powerful stuff. Now, I'm going to let you in on a secret. Use the GDC. I mean, why wouldn't we? We have this terrific, powerful calculator that we can graph things and find things like a rational root and use that to help us factor. And let me just show you how to do that real quick. So we add a graph page, and I'm going to type in my polynomial. 2x cubed minus 11x squared minus 11x plus 15. There's my graph. And what I'm going to do is I'm going to find the zeros. So we go to choice 6, analyze graph. We want the zeros. And I'm going to go until I find a rational one. If I find these others here and here, those are going to be big, long, Yankee decimals. They're going to be irrational numbers. This one clearly is rational. So what I can do at this point is I can jump right into the synthetic division using GDC. X equals -3/2 is a root. And I can jump up here to this synthetic division, get my factors, and find my remaining zeros exactly from this quadratic using the quadratic formula. So we have this great, powerful tool in our graphing calculator, but I think it's really cool to know how to do this without using your graphing calculator to see where these values are coming from and really look at it analytically and see the beauty of the mathematics.